This video was sponsored by Brilliant. We all know that computer processors contain circuits that perform mathematical operations. In the same way that there is a circuit for adding numbers, you might expect a processor to contain a separate circuit for subtraction. But what if I told you that computers do not actually need one? In today's episode, we are going to learn how computers handle negative numbers and why they do not need special circuitry to perform subtraction. Hi friends, my name is George, and this is CodeCrafters. For this video, it is important to understand how numbers are naturally represented in the binary system. So first, we need to recap how our own decimal system works. The word decimal refers to 10, meaning that we have 10 symbols for representing quantities, from no quantity at all up to 9 units. When we need to represent quantities greater than what a single decimal digit allows, we have no choice but to start combining those symbols, with each combination representing a specific quantity. With 2 decimal digits, we have 100 possible combinations, which we use to represent quantities from 0 to 99. When those combinations are no longer enough, we add a third digit. That gives us numbers from 0 all the way up to 999. The binary system works in exactly the same way, except that it has only 2 possible symbols, 0 and 1. These can represent either no quantity at all or a single unit. Because of this, as soon as we need to represent the quantity 2, we must start combining binary symbols. Instead of talking about decimal digits, in the binary world we talk about bits. With 2 bits, we can represent 4 possible values. When that is not enough, we use 3 bits, which allow us to represent 8 different values, and so on. This is usually known as the natural binary representation, because each bit directly represents a non-negative power of 2, just as each decimal digit represents a power of 10. For us humans, the problem with the binary system is that, because it uses only 2 symbols, its representations quickly become very long, even when the quantities themselves require only a few digits in decimal. Binary numbers are therefore generally not ideal for humans because they can quickly become difficult to read. Nevertheless, the binary system is used in computing because electronic components are extremely good at working with 2 distinct states. We have all heard about transistors, electronic switches that can be combined to create more complex components, such as logic gates. Those logic gates can then be combined to create even more complex components, such as this circuit, which can add 2 binary numbers. I have shown this circuit before on the channel, but here is a quick recap of how it works. In the decimal system, when we need to add multi-digit numbers, we split the operation into smaller steps. Each column effectively becomes an addition involving up to 3 single-digit numbers. 3, because the result from the previous column may have produced a carry that must be included in the next one. In the binary system, the addition of multi-bit numbers is handled in exactly the same way. We divide the operation into columns and add them from right to left, always accounting for any carry generated by the previous column. Therefore, if we can design a circuit that produces the correct outputs for every possible combination of inputs in a column, we can place several of those circuits together to add multi-bit numbers. That circuit is called a full adder, and it looks like this. Given 2 input bits and a carry-in bit, it produces a sum bit and a carry-out bit. To add larger numbers, computers place multiple full adders side by side, with each one handling a different column. The carry output from one column is connected to the carry input of the next. And just like that, we have a binary adder, in this case, a 4-bit binary adder capable of adding 2 4-bit numbers. Now let's talk a little about subtraction. Unsurprisingly, binary subtraction works much like decimal subtraction. The operation is divided into columns, but unlike addition, instead of dealing with carries, we deal with borrows. Once again, you might think that if we design a circuit that produces the correct outputs for every possible combination of inputs on a column, we could place several of them together to create a binary subtractor. And you would be right. In fact, that circuit looks like this. Given 2 input bits and a borrow-in bit, a full subtractor produces a difference bit and a borrow-out bit. Multiple full subtractors can be placed together to create a component capable of subtracting 2 4-bit numbers, a 4-bit binary subtractor. Unfortunately, we are not going to follow that path today. Although it may not look like it, introducing a separate subtraction component would add unnecessary complexity to a processor's design. You see, unlike addition, subtraction is not commutative. When we add two numbers, the result does not depend on the order of the operands. However, when we subtract two numbers, the order does matter. That makes circuitry to handle subtraction more complicated. For starter, when the subtrahend is greater than the minuend, the result will always be negative. And the natural binary representation we learned earlier does not account for negative numbers. Solving this type of operation also requires additional steps. When we do it by hand, for example, we may swap the operands, calculate the difference normally, and then make the result negative. We could theoretically do something similar in binary, but the negative sign would still be a problem. Computers can work only with ones and zeros. We cannot design a component that outputs the difference between two binary numbers, followed by a written negative sign as we do when writing a document or in a piece of paper. Nor can we store that result in memory as a sequence of bits preceded by a minus symbol. That is simply not how computers work. Whatever solution we choose must represent the negative number itself as a combination of ones and zeros. The most intuitive way to encode negative numbers in binary is the sign magnitude representation. Intuitive, like every single lesson on Brilliant. One of the biggest problems with learning in this AI era is that models can give you the answer before you have had the chance to actually understand the problem. That might help you finish an assignment, but it does not necessarily help you become better at solving similar problems on your own. On top of hundreds of interactive courses, Brilliant takes a different approach with Koji, its interactive AI tutor for students, including those at the college level. Instead of simply revealing the answer, Koji asks questions, breaks the problem into smaller steps, and guides you toward figuring it out yourself. He can even draw directly on the screen to help explain what is happening. That is the kind of tool I wish I had when I was learning some of these concepts for the first time, especially in those moments when I understood most of the topic but could not figure out exactly where I was going wrong. If you want to learn new concepts by challenging yourself while still receiving helpful guidance, Brilliant may be perfect for you. You can try Brilliant's tutor for free by accessing brilliant.org/coredumped or clicking the link in the description or scanning the QR code on the screen. Brilliant is also offering CoreDumped viewers 20% off an annual subscription. And now, back to the video. As I was saying, the easiest way to understand how negative numbers could be encoded in binary is through the sign magnitude representation. Imagine that we have a binary sequence of a fixed length, such as 4 or 8 bits. The sign magnitude representation uses the most significant bit, the bit on the far left, to represent the sign. A 0 means positive, while a 1 means negative. The remaining bits encode the magnitude using the natural binary representation. Not that difficult, is it? Well, modern computers generally do not use this approach for integer arithmetic. For starters, it makes simple arithmetic components, such as adders, unnecessarily complicated. But more importantly, and perhaps my least favorite feature of this encoding system, it allows 0 to be represented by two different bit sequences, one for positive 0 and another for negative 0. That may not sound like a major issue, but it is inconvenient, especially when performing comparisons. Suppose computers used this approach, and we wrote a line of code like this. Internally, it would effectively need to be treated like this. At the machine level, the processor would need to account for two different representations of 0 when what should conceptually be a single comparison is performed. For these and other reasons, sign magnitude representation is not commonly used for integers in modern general-purpose computers. Okay, but then how do modern computers represent negative numbers? Well, that is where 2's complement comes into play. Consider every possible combination of a fixed-length bit sequence, 4 bits for example. The first half of those combinations encode non-negative numbers using their natural binary representation. The second half encode negative numbers. For every positive number, its negative counterpart can be calculated by inverting every bit in its binary representation and then adding 1. Suppose we want to find the representation of negative 5. We begin with the sequence that represents positive 5, 0, 1, 0, 1. We invert all of its bits, and then we add 1. That resulting sequence represents negative 5 in 4-bit 2's complement. At first, this might seem like a completely arbitrary way to encode negative numbers. However, if you repeat the process for every value, you will notice that there is a very clear pattern. When we compare 2's complement with the sign magnitude representation, one of the first thing we can notice is that the most significant bit still hints if the number is positive or negative. But perhaps more obvious is that 2's complement has only one representation of 0. Not only that, but the bit sequence that sign magnitude would have used for -0 is instead used to represent an additional negative value in 2's complement. That is why, if we examine the values at the boundaries of the range, we find that the greatest negative magnitude is always 1 unit larger than the greatest positive value. In fact, you can test this yourself on your computer with a program like this. For those who are not familiar with C, what I am doing here is selecting 4 interesting sequences from all the possible 8-bit combinations. The first one, which contains only zeros. The 2 combinations at the boundary between positive and negative values. And the final one, which contains only ones. I then assign those bit patterns to variables that I have instructed the computer to interpret as 8-bit signed integers. When we print them, we can see the numerical values represented by those variables, or more precisely, what those exact bit sequences mean when interpreted as signed 8-bit integers. Here we can see what I mentioned earlier. With 8 bits, the negative side of the range extends down to -128, while the positive side reaches only +127. So first lesson learned today. When we declare a number as a signed integer, that number is encoded using 2's complement. Now, I want to show you what happens when we assign the exact same bit sequences, but declare the variables as unsigned 8-bit integers. This time, there are no negative values. Because we declared the variables as unsigned integers, every possible bit sequence is interpreted as a non-negative number using its natural binary representation. This also explains why some positive numbers that can be represented by an unsigned integer of a certain length cannot be represented by a signed integer of that same length. When a variable is interpreted as signed, roughly half of the available bit patterns are used to encode negative values. Consequently, fewer bit patterns remain available for positive values. In languages such as C, understanding this distinction is important because the compiler may not always warn us about the mistake we are making, as we can see in the example on the left. Anyway, I think the best way to become familiar with these encoding systems is to experiment with programs like these. Here, for example, I am doing the same thing with 16-bit and 32-bit integers. Once again, we can see that the magnitude of the lowest negative number is 1 greater than the highest positive number. For the third time, this happens because, on the non-negative side, one of the available bit patterns must represent 0. And now we understand what it actually means when we declare an integer as signed or unsigned. Now that we know how negative numbers are encoded, you might expect me to show you some impressive circuitry specifically designed to handle signed addition and subtraction. Unfortunately for you, and fortunately for me, I do not have to. Remember the binary adder I showed you earlier? It turns out that this is essentially everything computers need. Let me show you. When we pass 2-bit sequences into this circuit, the result is valid regardless of whether we interpret those sequences as unsigned or signed integers. Here, for example, if we interpret the inputs and output as unsigned integers, the circuit performs the operation 11 plus 18 equals 29. That result is correct. But if we interpret those exact same bit sequences as signed 2's complement integers, the operation becomes 11 plus minus 14 equals -3, and that result is also correct. Therefore, for any 2 binary sequences passed into the adder, the circuit effectively computes 2 different operations at the same time, one in the unsigned integer domain and another in the signed integer domain. This is incredibly important because it means that a computer's ALU does not need an entirely separate full subtractor circuit to perform subtraction. When a computer needs to subtract one number from another, it can rewrite the subtraction as the addition of a positive number with a negative number, and then use its binary adder to compute the result. Finally, I know that many of you like to experiment with the circuits I show on the channel. In some situations, you may encounter cases in which this circuit appears to produce the wrong result. Here, for example, the adder produces the 5-bit sequence 01001. In the signed integer domain, the operation being performed is 12 plus -3 equals 9, which is correct. However, in the unsigned integer domain, the circuit appears to be telling us that 12 plus 29 equals 9, and that is obviously not the correct result. This does not mean that the circuit is wrong. The problem is that the correct result, 41, cannot be represented using only 5 bits. A 5-bit unsigned integer can represent values only from 0 to 31. The binary result of the operation is actually 101001. The 5 least significant bits, 01001, remain in the output, while the additional bit appears at the carry output of the full adder responsible for the most significant column. When an unsigned result exceeds the range that can be represented using the available number of bits, we say that an unsigned overflow has occurred. Because that extra bit cannot be stored as part of the fixed width result, the processor uses the carry output to turn a status flag, commonly called the overflow flag. Software can inspect this flag to determine whether the unsigned result exceeded the available range. However, the same flag cannot be used to detect overflow in the signed integer domain. As shown right here, a final carryout may occur even when the signed result is valid. Also, signed overflow may occur without a final carryout. For signed 2's complement addition, overflow can be detected by performing an XOR operation between the carry leaving the most significant full adder and the carry entering it. Signed overflow occurs when we add 2 numbers with the same sign, but obtain a result with the opposite sign. You remember that I mentioned that in 2's complement, the most significant bit still hints if the number is positive or negative? Adding 2 positive numbers should not produce a negative result, so the flag warns us that the first significant bit in the result, which is 0, has overflowed. And adding 2 negative numbers should not produce a positive one. In the same way, the flag warns us that the first significant bit in the result, which is 1, has overflowed. The unsigned overflow flag therefore tells us whether the result overflowed in the unsigned domain, while the signed overflow flag tells us whether it overflowed in the signed 2's complement domain. And that is essentially how computers can work with both signed and unsigned integers using the same adder circuitry, and why they do not need a completely separate full subtractor circuit to perform subtraction. And let's wrap things up for now. If you'd like to support the channel, don't forget to check the sponsors in the description below. Or consider subscribing. And if you liked this video or learned something new, please hit the like button. It's free and that would help me a lot. See you in the next one.